For arithmetic operations using the binary numbering system, there are several simple rules which must be followed. There are 4 rules for binary addition. These are 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 0, carry 1. Let's look at an example for adding 1010 in binary with 1011 in binary. We have shown our example in both decimal and binary notation. We can see from the rules for addition that 0 plus 1 equals 1, so we place a 1 in the rightmost column. Next, the rules show that 1 plus 1 equals 0, carry 1, so we place a 0 in this column and carry 1. In the next column, we have 1 plus 0, and the rules show that 1 plus 0 equals 1, so we place a 1 in this column. In the last column, we have 1 plus 1, and we know that the rules say that equals 0, carry 1, so we place a 0 in that column. Since our problem has no additional columns, we will use the next most significant bit value, which in this case would be the 16. By converting our binary answer into decimal, we see that the binary number 10101 equals 21. There are also 4 simple rules for binary subtraction. They are 0 minus 0 equals 0, 0 minus 1 equals 1, borrow 1, 1 minus 0 equals 1, and 1 minus 1 equals 0. In our example, we have shown the decimal equivalent and the binary problem. Remember, we begin with the least significant bit and work toward the left and the MSB. When we subtract 1 from 0, the rule shows that the answer is 1 and borrow 1 from the next column. Therefore, we will place a 1 in this column and place a minus 1 in the next column. Since we now have a minus 1 and a plus 1 in the next column, this will equal 0. When we subtract a 0 from a 0, the rule shows the answer is 0, so we place a 0 in this column. In the next column, we again subtract a 1 from 0, which the rules show the result will be a 1, borrow 1. Therefore, we place a 1 in this column. In the next column, we have a minus 1 and a plus 1, so subtracting 1 from 1 gives us 0, making this column now 0 minus 0, which the rules show is 0, so this column gets a 0. In the last column, we have a 1 minus 1. According to the rules, the answer is 0, so we place a 0 in this column. When we convert the binary number 00101 into decimal, we find the answer is 5. Here we see the rules for binary multiplication. As you can see, 0 times 0 equals 0, 0 times 1 equals 0, 1 times 0 equals 0, and 1 times 1 equals 1. The process of binary multiplication is quite similar to decimal multiplication in that the multiplicand is multiplied by the least significant bit of the multiplier. However, the partial products are added at each step of the process. An example should clarify this procedure. In this example, we are multiplying 1101 by 100 binary. As you can see, the decimal equivalent is 4 times 13. First, we will multiply the least significant bit of the multiplier times the multiplicand. According to the rule, 0 times 1 is 0. 0 times 0 equals 0. 0 times 1 equals 0. And 0 times 1 equals 0. Now we will go to the next multiplier bit and perform the same process, but we will shift the first partial product 1 bit to the left. We see that 0 times 1 equals 0. 0 times 0 equals 0. 0 times 1 equals 0. And 0 times 1 equals 0. At this point, we add the partial products together using the binary addition rules. In binary addition, 0 plus 0 equals 0, so we will have zeros from the most significant bit to the least significant bit. Next, we multiply the most significant bit of the multiplier times the multiplicand, and we must also shift the next partial product one bit to the left from the previous shift. When we multiply 1 times 1, the product is 1. When we multiply 1 times 0, the product is 0. Again, we multiply 1 times 1, and the product is 1. And again, 1 times 1 equals 1. Next, we again add the two partial products using the rules of binary addition. Our answer is 110100 binary. When we convert this to decimal, we see that the answer is 52. Now we will examine binary division. The rules for binary division are the same as those used in the decimal system. For example, if we divide the binary number 1111110 by the binary number 110, the answer will be 10101. Let's work this problem to see how we acquired the answer. The smallest number that 110 will divide into is the first 3 bits of the dividend, which is 111. Therefore, we will place a 1 above the third bit and subtract the 110 from the 111. As you can see, this will leave a remainder of 1. At this point, we bring down the next bit, which is a 1. Since 110 will not divide into 11, we place a 0 above this bit. From here, we bring down the next bit, which is a 1, and place it to the right of our remainder. This gives us the number 111. So our divisor of 110 will divide into this number, so a 1 is placed above this bit, and we subtract 110 from 111. Once again, we have a remainder of 1. Now we bring down the next bit, which is a 1, and place it to the right of our remainder of 1. We see that the divisor of 110 will not divide into this number, so we place a 0 above the bit. From here, we bring down the last bit, which is a 0, and place it beside the remainder of 11. This now makes our remainder 110. Since our divisor is 110, it will go into the remainder 1 time, leaving a remainder of 0. Since we are able to divide at this point, we place a 1 above the last bit. To verify that our calculation is correct, we simply convert our binary number into its decimal equivalent. We see that the decimal equivalent of the binary number 10101 is 21. In Digital 1 of the You Can Do series, you learned how to convert from binary to decimal and from decimal to binary. You also learned that the binary system is the system most commonly used in digital circuits due to its simplicity in having only 2 states of energy. It is either on or it's off. It is very easy to make mistakes in addresses and information when using binary notation due to the large number of digits required to express a given quantity. Therefore, some computer systems make use of a notation called octal notation. In octal notation, a group of 3 bits is represented by a single digit. The octal system contains 8 digits, 0 through 7. As you can see, each digit in the 3-bit binary group carries a weight of 1, 2, or 4. Since each 3-bit binary group has a base of 8, they will increase from right to left by the power of 8. Thus, each group of 3 increases in value by a factor of 8 times the value of the previous group. Converting binary digits into octal notation is a very simple process. For example, to convert this 12-bit binary number into octal notation, first we must divide the binary bits into groups of 3, starting from the right. Next, we assign the weight values to each of the 3-bit groups. Then we add the values of each weight which contains a 1 for each of the 3-bit groups. At this point, we see the binary number 10011111001 converts to 4371 in octal notation. Now suppose we had only an 8-bit binary group of digits. As you will see, the conversion process is the same regardless of the number of binary bits. First, we must divide the digits into groups of 3, starting from the right. Then we assign weight values to the binary bit groups. As you notice, the most significant bit group only contains 2 digits. Basically, we could say this group does not contain a 4, so we will place a 0 below this weight factor. Next, we simply add the values of each weight which contains a 1 for each of the 3-bit groups. This shows us that the binary number 100111101 is equal to 235 in octal notation.